All right. On this right-hand side, what's the variable in my equation? X. So this is the variable we have to solve for, X. On my left-hand side, what's the variable in my equation? Sine of X. So I need to find the sine of X first. So I need to solve for the sine of X. That's my variable, right? I don't know what it is. So in this side, on the right side, how do I go about solving for X? Okay, so let's do one step at a time. Let's add 1. So let's do the same thing over here because it's an algebraic equation. I bring down whatever's there. I eliminate that. And now you said I do what over here? I divide by 2. So I do the same thing over here because that's what's in front of my variable is a 2. And I get the sine of X is equal to 1/2. And I get X is equal to 1/2. Okay, so my algebraic equation is done. I solved it. My trig equation is only halfway done. I solved the algebraic part of it, but I didn't solve the trig part of it. Because now it's asking for an angle whose sine is 1/2. And no restrictions. Any angle whose sine is 1/2. So I look at my quadrants. I did my algebraic part, now do my trig part. And I say, where is sine positive? 1 and 2. Well, sine is the x or the y? The y. So where is the y positive? 1 and 2. So I'm going to drop 2 triangles. It's the same as if I made my circle and just did this. So we don't have to make the circle, just drop the triangles. We kind of just cut to the chase. So we say, okay, sine is y over r. 1 over 2. Oh, I recognize this as my special triangle. What angle is this little reference angle? 30. How many times does 30 go into 180? 6. So this is going to be 6 pi over 6. This is going to be 12 pi over 6. So what is this first angle? Pi over 6, 1 pi over 6. And what is this angle over here? 5 pi over 6. Okay. Now, it says find all solutions. All solutions means this. I can come back around the circle again. I can stop here. I can stop here. Or I can go back around the circle all over again. Come back around, stop here. Come back all the way around, stop here. I can do this forever and ever, right? Isn't this a continuous curve? Even though my circle goes from 0 to 360, doesn't my sine curve go on and on and on and on and on? Aren't there like tons of them that have 1/2? Right? Even in the negative side, tons that have 1/2. So I have to have a way to do this. Generally, we do this real easy. We just go the positive route. We don't worry about the negative route right now. So I think of it this way. What is the period for a pi? How long does it take to complete one full cycle? That's the period for sine. Did I say pi? Sorry. What is the period for sine? 2 pi. So that means every time I go around 2 pi, oh, Chris, there's nothing. Oh, you're from last week? Yeah. Okay. How many days were you out last week?
Thursday and Friday.
Thursday and Friday. Okay. So every time I go around, it takes me another 2 pi. So if I take this and I add 2 pi to this, won't I get the next angle that comes around? Then I add 4 pi to this original angle? Forever? Kind of, but we're going to make a little saying like you did with the restricted things, with the reciprocal things. We're going to make a little saying out of it. But I just want you to see a pattern. So I notice every time I do this, I go up another 2 pi, right? So I can just quickly do this, because Amanda said, don't drive me crazy doing this whole thing. Why don't I say plus 2n pi, where n is any integer? Won't this cover all solutions? I'm going to get to that part. Amanda's just a little ahead of me here. So does this make sense? So if I put a 0 in here, I'm at the 0. Don't I get pi over 6? If I put a 1 in here, I'm at the 2 pi. If I put a 2 in here, I'm at the 4 pi. True? 3 in here, I'm at the 6 pi. True? So we agree that this works? So now I can apply the same thing to this guy. What did I say? 5 pi over 6? Now, even though I say n is any integer, it's giving me all even ones because why? Because I multiplied it by 2. Okay, so I'm jumping there. Is that today's work? Oh, you have an extra? Perfect, thanks. Okay, so, makes sense? So all we did was this. Nothing crazy. We took an equation. We said, oh, this is an algebraic equation. It has a variable, one variable. I can solve for one variable. I solve it. I come down here. I did solve it. I found the sign of x. That's what I had to do. But now I have the trig part of my equation. What angles have the sign of 1/2? All completely the opposite of restricted angles. Every possible angle I could get. So if this tells me all solutions, I need to do this part of it. I need to qualify this. It's based on the period of that function. Now, sine has a period of 2 pi. Every 2 pi I'm going to circle around. Tangent has a period of pi. So it's going to be a little bit different with the tangent one, but we'll do one of those. Everybody okay with this so far? Stop me if you're not okay, because if you haven't seen these, they might look a little bit strange. All right, so let's try the next one. Okay. We have another equation. And here, what is my variable in this equation? Sine of x. My variable is the sine of x. So I'm going to take that out for a minute and do this. How would you solve this equation, this algebraic equation? Which would mean I would have to subtract this x, right? And then you would divide by -2. So did you solve for x? Good. Okay. We're going to do the same thing here. I'm just going to bring this down here because there's no room up there to work. So my variable in this case is the sine of x. So I'm going to get all my things over there. You cannot separate sine x. You can't get that x out of there. So I'm going to put a 1 here, if that's okay with you. I'm going to subtract 1 sine x from both sides. And just like you told me up there, let's divide by a -2. So now I solved my algebraic equation. I've got an angle whose sine is negative radical 2 over 2. Sound familiar? It's the reference angle. 45. We can unrationalize this if you like. Or you can leave it like that, and you can find the third side. Let's look at sine first. Where's sine negative? Where's the y negative? What quadrants? 3 and 4. So drop your triangle in 3 and 4. So now, if you go with, I'll do this one with the radical 2, I'll do that one with the 1. So here's the 1 over the radical 2. So yeah, that tells me 45 degrees. This, if you didn't see it, this is your y, this is your x, I'm sorry, your radius. To find my x, I'm going to use Pythagorean's theorem. It still works. You can do it either way you like. This is going to be 2 plus x squared equals 4. X squared is going to equal 2. So therefore, x is going to equal, when I take the square root of both sides, x is going to equal radical 2. So if you're looking at this, and both of your legs are the same, what's your reference angle? 45. So either way you want to do it. If you unrationalize it first, that makes life easier. Okay, so now, how many times does 45 go into 180? 4 times. So this is 4 pi over 4. Doubled, 8 pi over 4. So in my realm of 2 pi, how do I name this angle? 5 pi over 4. Good. How do I name this angle? 7 pi over 4. Okay, so that's in my 360 circle, my 2 pi. Now again, the period is every 2 pi. So I have to go around, completely go around 2 pi, completely go around this guy 2 pi. So I say plus 2n pi, where n is any integer. Agree? Agree? Where n is any integer. Okay, so that solves all solutions. Now they want the solution within 4 pi. So how many more times do I have to go around this thing?
Wait, would it be right to put just plus n pi where n is any even integer?
Plus n pi where n is any even? Yeah, but we usually don't say that. I guess it would work, but it's going to mess us up when we go over here. So try to stick with this because we're going by a period. Yes. Yes. Okay, so now I need solutions within 0 to 4 pi. Just those. So I already got 2 of them. I got an x equals 5 pi over 4, and I got an x equals 7 pi over 4. We have a couple of ways to do this. First way, since you're only going around one more, you have a little pattern right here. This is 8. What would this guy be next time around? 12 pi over 4. What would this guy be next time around? Double this. 16 pi over 4. You're going every 4, right?
Oh, yeah.
So now, the second time around, what would this angle be over here? Third quadrant. 13 pi over 4. 1 more than 12. What would this guy be? One less than 16. Okay, that's one way to do it, since you're only from 0 to 2 pi. Another way to do it is this way. If you're only going to 4 pi, that's what I usually do. I just keep my pattern going one more time around. If you're going to 8 pi, 12 pi, or whatever pi it says, this would work too. So you're adding 2 pi every time, right? But you can't add 2 pi to this guy because it has a denominator. So if I want to make this the same denominator, how many fourths is 2 pi? I don't know. So let me convert this to the same denominator. So how do I convert my numerator? So I multiply it by 4, and what do I get? 8 pi over 4. And 8 pi over 4, isn't that still the same as 2 pi? I'm still adding 2 pi. So now when I add these, don't I get 13 pi over 4? So if I come down here and this guy is 7 pi over 4, aren't I still adding 8 and giving me 15 pi over 4? Convert this first. Since you're adding 2n pi, you're going to keep adding 2n pi forever. If I do it again, I just add another 8. I'm at 21 pi over 4. I'm at 23 pi over 4. I'm just adding 8. And the reason I added 8, because how am I going to add 5 fourths plus 2? I can't. So I just convert this to a same denominator, whatever denominator this is. So now, can I add 5 fourths plus 8 fourths? So all I have to do is keep adding the 8 all the way around, which makes sense, right? Okay? So you have a couple of different ways you can do this part of it. Again, if it's only another choose another cycle around, I would just cycle that part. But this part works all the time. What you want to do is have a cutoff point. So say, where's my cutoff point? So if I'm at 4 pi, I can't go more than 16 pi. Are my values within 16 pi? Make sure you don't extend past there. Like, when do I stop adding? This one was easy because we only went another 2 pi. We could obviously figure, if we had 2 angles in 2 pi, how many angles are we going to have in 4 pi? 4 angles. That was kind of easy to see, right? Sometimes it's not as easy, so set this limit up here and don't go past that limit. Well, we'll see some of those. Okay so far? Okay. No frowning. This is not so bad. Set my board. Somebody must have been playing with it. Those little nasty ninth graders that come in here. Alright, here's the tangent. What's the variable in this equation? Tangent x. So again, if I replace my variable, how would I solve for x in that equation? Subtract 3 and divide by 3, right? So you get x is -1. Subtract 3, divide by 3, right? So I'm going to do the same thing here because this is my variable. This whole thing is my variable. So I'm going to subtract 3. I'll write this out. And I'm going to divide by 3. And I get a tangent of some angle equal to -1. Is that right? This is the one you guys mess up on. 45. This is not a quadrantal angle because it's a tangent. Okay, so now, tangent. Tangent is y over x. One is positive, one is negative. So which quadrants have 2 different plus and minus signs in them? 2 and 4. Okay, so these are the same signs in 1, the same signs in 3. So aren't those where my tangents are positives? Okay, so I label this 1 over 1, and I know this is a 45-degree angle. 45 goes into 180 how many times? 4. So this gives me 4 pi over 4. This gives me 8 pi over 4. Everybody still okay with me labeling it like that? To find our angles works so much easier than converting your angles, right? Okay. Catching that pattern? All right. Find all solutions. My first angle in this guy is what? 3 pi over 4. My second angle is 7 pi over 4. Okay, so I want all solutions. So normally we say plus 2n pi, right? But what's the period for tangent? Pi, right? Isn't it just pi? Doesn't it come within those little -90 to +90? Isn't it every pi? Remember, this is different. This is not the sine and cosine curve. It's that little spaghetti piece that fits in here somewhere. Okay? It only has a cycle of pi. So here's a little trick with this guy. I can take just this one and only go pi away from it. If I just add pi, isn't that pi is 180? Isn't that a half of a circle, 180? If I add another half a circle, don't I get here, then here, then here? So this guy, I can say n pi, where n is any integer. Because its period is pi. So only the tangent works this nicely. No, I shouldn't say that. We'll see other things. Now, if I had a situation where I did all 4 quadrants, say this came out to be plus or minus 1, and I had to do all 4 quadrants, just if. And this was pi over 4. And this was 3 pi over 4. And 5 pi over 4. And 7 pi over 4. And I wanted to do all solutions. I could come here to this one, the first one I hit, and add pi to that. So I would take this one and do the plus n pi. That would take care of this guy and this guy, wouldn't it? Half the circle around, half of 2 pi is pi. Then I could come to the next one I hit that I didn't keep track of. That's this guy, and add n pi. Doesn't that take care of this one and this one? Okay, so you want to hit the first two that you hit. I don't want to hit this one and this one. Because then this one, I wouldn't come back and never hit this one. Because I'm only going to do this a positive times. We're not going to do the negative times on this. So I want to make sure I hit the first guys. Alright, so if I'm doing all solutions in 4 pi, again, you have a choice. You could go through here, and you could say, okay, this is 8, this is 12, add another 4, this is 16. If it's only going to go to 4 pi, this works out nicely. So I've got all solutions, 3 pi over 4, and then what after this? I got this and 7 pi over 4. Let's start like this. If I come back around, and this is 12 pi over 4 over here, what's this guy? 11 pi over 4. If I come back around, and this is 16, what is this guy? 15 pi over 4. Agree? That's probably a 4. That's probably just my messy handwriting there. I'm right at the edge there, so I'm afraid where that little border is. Because I think this is so off, because I can't get to this piece. So now, you could do it that way, or you could do it the other way. Plus n pi. I just have to take this, and I have to turn this into, and n pi will be like 1 pi, 1 n pi. So I just have to turn this into fourths. This is a 1. So it just gives me 4 pi over 4. So I can add 4 every time. So I can do this. 3 pi over 4 plus 4 is 7 pi over 4, plus 4 is 11 pi over 4, plus 4 is 15 pi over 4, and I stop. How do I know when to stop? I set this to fourths. This is easy. Yeah, some kids don't see this, they see the other way. You're just going to take, and this has a period, tangent mark's different, it has a period of pi. So I really only needed to do one of these, didn't I? I only needed to do 1 and 2 pi, right? Because the other one is the 180 degrees away from that, pi away from that. So if I start with this guy and I just say add n pi, I'm adding 1 pi to this. Can I add 3/4 plus 1? How do I add 3/4 plus 1? Without your calculator. I need the same denominator, so I'm just converting this to the same. Isn't 4 over 4 the same as 1? So now just don't I add my numerator all the time? So start with 3 pi and keep adding 4. 7 pi, 11 pi, 15 pi. If I add 4 more, I'm here. But you only wanted to go to 4 pi, which is the same as 16 pi over 4. So this guy is out of my domain. I didn't want that one. I only need 4. I get 2 and 2 pi. I should get 4 and 4 pi, right? I could also stop when I count 4 angles. And I know how to stop. So there's a lot of ways to do this. But the key is finding the all solutions way first. And then finding the exact solutions that you need. It means dealing with fractions. It means converting that denominator. Yes?
So, do you have to add all this to the 7
No, because we only had one cycle. We only had one angle that we had to keep track of in tangent because what's its period? Pi. So they're completely opposite each other. In the sine and the cosine, do you remember when we did the sine and the cosine ones? We didn't do a cosine, I think we just did a sine. The sines were like this. We can't add 90. 90 doesn't work. So these are not opposite each other. So we couldn't do that with sine because the sine period is 2 pi. I can't add 90 because I can't come down here. I only could be up here. So the sine period is 2 pi. The tangent period is pi. So my tangents are opposites the same. Positive, positive, negative, negative. My sines and my cosines are not. That's why we can't do this for cosine, because their period is 2 pi. But the period for tangent is only pi. So this is my answer for all solutions. So I only have to take that one and figure out in fourths, what do I add for pi? In fourths, 4 pi over 4. You're just converting your denominator to make your numerator add easier. Okay? Makes sense? Any more of these guys? I think we have one more. Okay, one more. Good. This is a good one. Am I leaving anybody in the dust here? So do you remember doing this at all?
No, we
We didn't do this.
Not at all. Okay. All right. Here's my variable. Let me rewrite this a minute. 3x squared. Here's my variable. I got a square in there, right? How do I solve this algebraically? Add 1, divide by 3. Okay, so far so good. Then what? Oh, square root. So what is the square root of 1? 1. So is that my answer? Plus or minus. Good. When you undo a square, you get a plus or minus. When the square root is there, you get whatever sign's in front of it. But when you undo a square, you get a plus or minus. So now when I come to this guy, I'm going to do the same thing you told me. Add 1, divide by 3. Then I'm going to take the square root. So now, algebraically, I am finished. I get the same answer that we got there, right? The algebraic part is finished. What I have left to do is the trig part. So I say, tangent, plus or minus. All 4 quadrants, right? All 4 quadrants I'm using. I got plus or minus. So it's positive in 1 and 3. It's negative in 2 and 4. Oh, so that gives me all 4 quadrants I'm using. Agree? Okay. So now, I'm not really sure my angle, but hopefully it's a special one. So I say y over x. 1 over radical 3. Do I recognize this as a special triangle? What's my reference angle? 30. So 30 goes into 180 how many times? 6. So this is going to be 6 pi over 6. This is going to be 12 pi over 6. Now, if I start like this, I have 4 solutions. Okay, I'm just going to write out the 4 solutions for now. This is pi over 6. This guy in second quadrant is what? This guy in the third quadrant is what? And in the fourth quadrant? Okay, so I have 4 angles that make this true. Okay, and on my calculator, if I'm not seeing that, I can put this in. Let's leave my mode in. Oops, I got the pen in. Let's leave my mode in radians. Let me check this answer. This looks a little bit strange. So let me just put one of these in. 3 times the tangent of, let's pick one. Let's pick 7 pi over 6. Maybe not. I can't get my pi sign out here. Something's wrong with that side of the board for some reason. Oops, I went to the wrong one. Okay, and we have to say squared. Then we're going to say minus 1. What should this come out to be? 0. Yep, it works. So let me check another one. I checked 7 pi. Let me just check 5 pi, just for the heck of it. Because each quadrant, I can obviously know my opposites will work, but will 5 pi work? Yep, 5 pi works. So I'm in good business here. I know they're algebraic equations. You can check them anytime you like. Or put your mode in radians, put your mode in degrees, and check it with the degree angles. Okay, so now, I want all solutions. Now again, this is what I was talking about before. Start this way. You hit this guy first. That's this one. If we add 180 to that, don't I come here? And then here? And then here? So should I hit this one and this one with the same n pi, right? So I'm going to take this guy plus n pi, where n is any integer. That takes care of 2 of them, this one and this one. So as I circle back through my triangles, I hit this guy next. I got to hit the first one. If I hit this last one, I'll never go back to the first one because it's doing positive n pi's. I only did the positives. So I get this guy, which is 5 pi over 6. So that takes care of this one and this one. So these guys, I don't need. If I was just looking for the solutions within 2 pi, yeah, I have 4 of them. I don't need to do my plus n pi. But if I'm doing all solutions, do I need to say all of these plus 2n pi? No, because your period of tangent, the period for tangent is pi. So every 180 degrees, it'll hit the same thing. Isn't the tangent in quadrant 1 positive as well as the tangent in quadrant 3 positive? The tangent in quadrant 2 is negative, the same as the tangent in quadrant 4 is negative. So every 180 degrees on tangent and cotangent works the same.
Like, say you forgot like a test and we're all 4 plus 2 pi, so right?
It's not wrong. It's not wrong, but I would prefer you get it this way. Yeah, I would prefer this. But it's not wrong. So we go with this. Okay, a little bit different. It's a little different in finding these. So you should be able to do